Continuing with the story of using bases for transformation matrix, using a basis to get the matrix for a transformation, let's say that, and the change of basis theorem. Here's the schematic picture that we've got so far. We've got a vector space phi, a transformation from that space to itself, and it can get more complicated with different vector spaces, but this gets the main thing. We've got the coordinate map that takes a vector and gives its coordinates in the basis B. Same deal over here. And then we have the matrix version. A map from Rn to Rn really is a matrix. And that's the matrix A, which is also would be called the matrix of T in the basis B. Okay. And so, for example, if you've got some vector W and U, oh, it's right here, U equals T of W. I'll put it here too. And U is the output of the transformation applied to the input W. Then we'd like to know what's the corresponding version of that with matrices and column vectors. Well, let's say X is the coordinate version of W, it's just CB of W, and Y is the coordinate version of U, then Y is just equal to AX. And that's another way of saying that A is really accurately representing this transformation at the level of column vectors. Okay, so let me do an example of that. I want to emphasize that V can be some abstract space sometimes, and so let's say V is the set of polynomials, and to make it finite dimensional, of degree less than or equal to 3. Okay, and let's say T of a polynomial, let's say F, is F prime, the derivative. That's a linear transformation. That's a fundamental fact about the derivative. And then we could ask, given any basis for these polynomials, we could ask for the matrix of the derivative. Okay, so let's say one matrix might be a pretty obvious choice: 1x, x squared, x cubed. Okay, and then we'd like to figure out what the matrix of the derivative is in this basis. And what are we supposed to do? We're supposed to take the derivative of each of these basis vectors and then express it in terms of the basis vectors again. So T1 is 0, which is 0 times 1 plus 0x plus, okay, so it's all zeros. Well, I'll just write it out. 0x squared plus 0x cubed. Okay. T of x is 1, which is 1 times the polynomial 1 plus 0x plus 0x squared plus 0x cubed. T of x squared is 2x, which is 0 times 1 plus 2 times x plus 0x squared plus 0x cubed. And T of x cubed is 3x squared, which is 0 times 1 plus 0 times x plus 3 times x squared plus 0x cubed. Okay? And so how does this go into the matrix? We just have to make sure it's either the sort of matrix that we are kind of visually seeing here or its transpose. We just have to be careful about that. And remember, back to the original definition of matrices for a transformation in the standard basis, it's that when you put in the different inputs, you're actually calculating the columns. And so different inputs correspond to different columns, different outputs correspond to different rows. And that's still true here if you unpack what I was saying last time. And so we've actually written down the transpose of, if you just sort of delete all the basis things, it's actually the transpose. So that's a little bit annoying. So the matrix of T in that basis B is going to be the matrix where that's the first column, that's where that first basis vector went, expressed as the coefficients in terms of that same basis. And then the next one is 1, 0, 0, 0, and then 0, 2, 0, 0, and then 0, 0, 3, 0. Okay. And that's actually a very nice picture of the derivative applied to polynomials. That it's an upper triangular matrix with just this 1, zeros along the diagonal, and just this increasing series of numbers, 1, 2, 3. And of course, you can guess what's going to happen for higher degree polynomials, 1, 2, 3, 4, 5, 6, 7, as far as you want to go. And then zeros above that. So it's really a nice thing we've discovered, is that if you understand matrices that look like this, then in principle you understand calculus for polynomials, which is not a bad thing to understand. Okay, so We could also have, what if we had like chose another basis, B prime? Let's say that basis might be, um, let's say 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed. Maybe there's some reason why we'd want that basis where each time you do a new basis vector it kind of grows. Hopefully it's clear that these guys are linearly independent and span the space of three-degree polynomials. It's pretty clear how to get the old basis out of this guy, and this guy is actually written in the old basis, so you can go back and forth. Okay, so we could get the matrix of T in this new basis, B prime, directly just from the definition, and then eventually, if I feel like it's worth the time, this marker's not getting, it's not good. We could think about this as a change of basis example as well. Okay, so T of 1 is 0. T of x is 1. Okay, that's already written in the basis. We can figure that out. The other ones will be a little harder. Oh, sorry, T of 1 plus x, but it's still 1. T of 1 plus x squared is equal to 1 plus 2x. Okay, we got to write that. That's 1, that's 2, let's see, it's minus 1 plus 2 times 1 plus x. Okay, so I'm just doing this by hand because it's not super hard. And every time, in principle, though, a lot of these calculations might require row reduction, solving systems, matrices, that kind of stuff. Yeah, so that's 2x plus 2 and then minus 1. That's good. And then t of the last one, I didn't do this beforehand. I figured it would be simple enough to do by hand, but maybe I'm wrong. That's 1 plus 2x plus 3x squared. Okay, so we need to use 3 of these guys, right? So that's 3 times 1 plus x squared. Can you read that? Okay, I think so. And then that gives us a 3x, but we only want 2x, so we're going to subtract off a minus 1 and 1 plus x, and then that gives us 3 minus 1 is 2, but we want 1 minus 1. Okay. Okay, so now, oh yeah, I could just almost use the whole thing. The matrix of T and B prime, then, is that first thing just gave us zeros, so that's still the same. The second basis vector was just that first basis vector. The output was just that first basis vector. T of the third basis vector was minus 1 times this guy and 2 times this guy and zeros. And then T of that last basis vector turned out to be a little more complicated. It's minus 1, 3, 0. Oh, okay, so we still have the 1, 2, 3s, and then we're just getting these minus 1s because of the different basis. Okay, so there's a couple of examples of finding the matrix of a transformation in a certain basis. Okay, so now back a little bit to the theory. We've now got a situation where we did the same matrix, the same transformation, but in two different bases. Is there a way to go directly? Is there a way to go directly from that matrix we had for B to this matrix in terms of B prime without just going back to the transformation and redoing the definition? And there is, and that's really important. Okay, so the first thing is simply how do you relate the bases to each other? Okay, so here's where we have this diagram, another diagram. Okay. We want to, again, emphasize this point of view. Everything is a space or a map. It's a very, very powerful modern point of view. And here's what we want to do. We've got the same vector, say. Let's not worry about transformations yet. We have the same vector, let's say W. Okay. And we want to express that as a column vector in terms of the basis B. Okay. And, oh, again, this thing's fading out. I think the gooseneck is getting a little weird. Okay, now you can see better. Yeah. And then we also want to take that and express it in terms of the basis B prime. We're going to get different numbers. We want to figure out what's the map. Let's see, which way do we want to go? P is going to go, he's got P going from B prime, actually. It's a matter of taste where you put the primes and everything. Okay. We'd like to say, suppose you had the column vector in B prime, can we just go directly to this column vector without going back to the abstract vector space V, or the physical geometric vector space? Okay, and that's not too hard. Okay, so the first thing you want to do is the goal eventually is to take a random vector and compare how it's described in B prime versus B. But we should probably start out by taking a specific vector, one of the basis vectors. Okay, so just because it's going to work out with his notation, we're going to take, let's say, B is these vectors v1 through vn, and B prime is v1 prime through vn prime. Maybe totally unrelated, even though I'm using v for both, just two different bases. Okay, and so then what we want to do, very much like what we did with the matrix, with the linear transformation, we take one of the vi primes, and of course, because b is a basis, we can express that in terms of, I'm going to put just little slots first of all, in terms of the old vectors, plus slot v2 plus dot 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 plus slot vn. Okay, now we just need to name these guys. Okay, now for every vector, very much like what we were doing at the start of the first video, for every vector in this basis, I'm going to get n things. So I'm going to get an n by n matrix. Oh, so everything's an n by n matrix. Surprise, surprise. Okay, and we'll call that P sub, and then it turns out, oh sorry, this is a J again. It's very easy to get rows and columns confused. And then we'll call that P1J, P2J, plus PNJ. Very, very similar. Okay, so this is interesting what's going on. The same kind of technique keeps getting used over and over again. Take something from one world, express it in terms of the other world. And in the previous video, we were having a transformation where we took an input and an output. So there's actually some geometric stuff happening, but the basis was the same on either end, the input and output. This is the opposite. Here, nothing's going on. I'm taking the same vector and expressing it in two ways. I'm not doing anything to Vj prime. I'm just letting it sit there, but then I'm insisting I want to express it in terms of the other basis. So it's a difference between interesting geometric transformations happening, going back and forth, and expressing it in a single basis versus comparing two bases, but I'm not trying to actually analyze the transformation yet. When we put it together, we'll get a more complicated kind of combined diagram that combines this diagram and the other one, and we'll see how that all comes together. Okay, so that's the definition of these guys, and so that defines a matrix P. Those are the coefficients of a matrix P. And we're doing it column by column. So the jth column is going to be how the v primes get expressed in terms of the v's. Okay, so that defines a matrix P, and the claim is that that's exactly what fits in here. Okay, so the claim is that if I take a vector v and I express it in terms of the vector w, let's say, because I don't want to confuse it with these basis vectors. I express it as a column vector in terms of the b prime basis, and then I just hit it with the matrix P, then I get the column vector version in this other language in terms of the other basis of the same vector w. So nothing's being done to the w here, but P compares and changes between the bases. So that's a change of basis matrix. Okay, the proof of that is very, very similar to the proof I had with all the sigmas that we had before. I'm not even sure if I want to do it. I think I'm going to save it. Okay, so it's very, very similar, and it's similar to what's in our book as well. But that's the idea. So let me draw the big diagram. Okay, so let's leave that as an unproved claim. We'll see if we need to go back to it. I don't want to make this just hours and hours of video. It's an important topic, but I don't want to make each video too long. So here's the master diagram. We're now ready for the master diagram. It's very cool, and it might be a kind of, God, none of these markers are working very well. Oh, that's better. Okay. It might be a bit sophisticated to talk about it on this diagrammatic level, but it's so cool, and it's such a great introduction to how modern mathematicians think. Okay, I'm going to draw this big diagram. Bunch of spaces and maps. And so it's got a square in the back here, which is taking a transformation from v to v and expressing it as a matrix in the basis B prime. And this very, very slick way of saying that that is the right matrix is to say that if you take a vector, do the honest geometric operation to it, reduce it to numbers, or reduce it to numbers and do this matrix on it, which is just arithmetic, you get to the same place, the same n-tuple of numbers. To say that that diagram commutes, that square, taking any input here and going this way or this way gets the same answer, is exactly saying that this is the matrix of T. Okay, so it's somewhat more, there's a cooler way of saying that. Now, this triangle here is the triangle I just had before, where you've got one vector and you don't do anything to it, you just express it in the two languages. You can express it as a column of an n-tuple of vectors here and a column vector here with B prime, or you can use the B language. And then we discovered that, and this is the claim I just said, is that one way of describing the definition of P we just gave is to say that this triangle commutes. That if you translate it into numbers here and then use the quick and dirty translator from numbers to numbers, you'll get the correct B version of V. And then there's the same thing we can do on the output, though. Okay, we can do that here. Maybe not quite so long. There's going to be an output of T. So if like this is W as the input going to over U, where U is just short for T of W, then I can take U and do the same thing. I can express it in B prime language, or I can express it in B language. And again, there would be a map here going for, this would be P. But you know what? I'm going to actually go the other way. Well, what the heck is that going to be? That's going to be P inverse. If instead you take the Rn, the B version of it, rather, and then want to translate to the B prime version, hopefully that's pretty clear that you should use the inverse matrix, the inverse change of basis matrix. And which one's P, which one's P prime is just a matter of convention of where you put these primes. P and P inverse. It's just a matter of where you put these primes and how the labeling it goes. But for what I've given you, it's the correct stuff. Okay, and then here is the matrix. The reason this is dotted is it's kind of in the back of this prism. It's like a prism diagram. So triangle, triangle, and then square faces. Okay, and so now we've got this face here, where ignore the B prime for a minute. We've got this vector U in V. We could use the B version of that, and we could try to figure out how to do the transformation, the geometry, in terms of the B numerical language in Rn. And that's this guy. So there's this slanty square face here. There's a back square face. Those are both how you translate T into matrix language. There's these two triangles on the left and right, which are comparing for just the same vector how the coordinate versions of that vector look. And now the key is this bottom square. This bottom square doesn't talk about V at all. It gets so totally away from the abstract vector space. And it just says, okay, I've got a column vector in here, which secretly we are interested in because it's the, say, the B prime version of this honest-to-God geometric vector W. I'd like to know what's the comparison between taking that and doing the B prime version of the transformation T. What's the translation between that and the B version? How are these matrices related? Well, it's the same thing as asking, what if I took this guy and translated it into the B language, that's over here, a new column vector, take the B version over here, and then you've got the B version of the output, and then you translate it back into the B language. And so the claim is simply that this square commutes. That's the change of basis theorem. It says that if you want to calculate, say, the B prime version of T, and suppose you have this matrix, and you have this matrix, and you have this matrix. Oh, you've got three sides of this square. Oh, okay. So this is just going to be P inverse TB B. This is just a statement about matrix multiplication. So this is something you could program on a computer that doesn't understand about abstract vector spaces. Okay. And so it says that in principle, if you've got the T version, the B version of the T matrix rather, and you've got the change of basis matrix, then you just put P on one side and P inverse on the other, and you get the B prime version. So let's see how that diagrammatically works. It's saying that if you start here and you do P, and then you do TB, remember composition reads right to left, it's kind of weird, and then you do P inverse, that's the same thing as what would happen if you took the input here and multiplied it straight by t by the b prime version of t. And that's just saying this is an equation of matrices. So I can get to the specifics of the proof in the next video, but in the next video I think I'll start out with just an example to make this more concrete. This diagram's getting awfully busy with all my decoration and everything, but I want to just tell you that the proof actually is just staring at the diagram. It's a very cool way to think about it if you're ready for it. I've asserted that these triangles commute, that if you go from here to here or directly or indirectly, you get the same thing. Now, I didn't prove that one, but if we assume that, then that triangle commutes as well. So if you go from here to here or here to here indirectly, it's the same thing. Okay. What else do we know? That this front square commutes. That if you take W and you express it in the B language and then do the transformation in the B language, it's the same thing as doing the honest geometric transformation and expressing the result in the B language. That's what we proved last time. And then the same thing is true for B prime, which is this back square. Okay. What do we want to know? We want to know if the bottom square commutes, because that's really the thing that's really just something about matrix algebra, saying that a certain two mappings of Rn, linear transformations of Rn are the same, is really saying that two matrices are the same, and that's what this says. Okay, well, let's take this guy, something in here. What we want to know is we take anything here, and we want to know if we go this way or this way, we get the same thing. Oh, actually, if you go this way, that's this guy, or this way, you get the same thing. Well, you know what? It's probably a little easier to express this as P TB prime is that equal to TB times P. It's the same thing, just multiplying this guy. So that's saying if I start here and I go around these two sides, or if I start here and I go around these two sides, do I get the same thing? Well, everything in here, every column vector in here comes from an honest vector up here. And we know that if we take this vector and we go down here, actually we go down here and then over here and then over here, what is that the same thing as? That's the same thing as cutting off this corner and going to here, okay. And then that's the same by the commutativity of this square. It's the same thing as going over here and over here, okay. But that's the same thing as going over here and here and here. And then we know the back square commutes, so that's the same thing as here, here, here. So what it turns out is that anything up here, if it go this way, this way, this way, it's the same as going this way, this way, this way. Okay. Well, the only thing that's different about that, this guy wasn't different in those two paths. The only thing that's different is that I went around this corner, these two sides of the bottom square in one, and I went these two sides of the bottom square in the other. And because everything in here comes from some vector up here, that basically proves that these two ways are the same. I think that's probably a little advanced for what we're doing, but that's how that's definitely how a mathematician would look at this and say, oh yeah, okay, totally, it makes sense, because everything else in the diagram commutes, so this bottom square has to commute as well. But we can prove it more in terms of summations and sigmas and stuff like that. Okay, that was again longer than I expected, but it's cool stuff, and we'll do an example in the next one.